Okay, and welcome to section 2.4 of our pre-cal notes. Here we're going to be talking about piecewise functions and how we define different things. So the first page of our notes is just a review of all the functions we studied in Algebra 1. And I just want to point out a couple of things here. We've given you the set notation and the range for each function. Obviously given you the parent function. And remember, parent function is the simplest function of that family. All of the others will be babies of this or branch off from it. And at the far right is our transformation equation. This is given in the Algebra 2 notation, Algebra 2, which has A, B, this one right here should be a C, so let's correct that on your quadratic. It should be X minus C, and all of these are the same. Our C value is how far we translated left or right. D was how far up or down. A gave us the vertical stretch or compression. And B gives you the horizontal stretch or compression and reflection. So they're all defined down here. As we move into pre-cal and higher level maths, I just want you to be aware that in some math, instead of saying C, they will use the letter H. So they do the exact same thing. Letter D in upper level math is often a K. So just keep in mind that C and H do the same thing. D and K are the same as we go forward. Okay, so now let's take a look at these notes. A function is said to be continuous, and hopefully that word sounds familiar, if the graph has no gaps or holes, and it can be drawn without lifting the pen or pencil from the paper. So the main thing is if you can draw your whole graph without ever lifting your pen or paper, it's going to be continuous. A function is discrete if the graph has gaps or holes, so that you cannot draw the whole thing without lifting the pen or pencil from the paper. Okay, so here's something new. We have seen this very briefly in Algebra 2 when we looked at absolute value functions, but we're going to look at it in much more depth right now. This is what's called a piecewise function. So a piecewise function is a function that has multiple definitions depending on what the domain is, so what x values you're looking at. So for example, for this function f, when x is between -3 up to +1, this is the function we're going to graph. If x is equal to 1, then I'm going to graph this point. X is 1, y would be 2. When x is greater than 1, so that means for any x value bigger than 1, I will graph this. I will square my x value. Okay, so it just means we have 3 different functions to graph, but notice the domains do not overlap. So if I want to find f of -2, that means I need to plug -2 into this function. So here's a little bit trickier. I can't just plug it into all 3 spots. I have to see where this x value falls. It's not greater than 1. It's not equal to 1. It falls in this part. So that means I have to use this function. So f of -2 is equal to -2, then plug my value in there, -2 plus 1. So -2 times -2 is +4 plus 1 is 5. F of 1, that means I'm plugging the value of 1 in for x, does not fall in the first definition because the x is not in that interval. When x equals 1, that's bingo. So when x equals 1, my function is simply just the number 2. Doesn't take work. Okay, and the final one, when f is equal to, when I plug 2 into my function f. So again, we look to see where the 2 falls in terms of the different domains that are listed. So it does not fall in this interval. It does not equal 1. X is greater than 1, so I need to use this function, so x squared. So I'm plugging a 2 in, so I square that and get +4. Okay. So again, the key here is looking at the x value you're plugging in and seeing which interval it falls in. Okay, determine the domain of f. Well, so what's our smallest value of f? Well, the smallest looks like is -3 and it goes up. Let's see, it goes to 1, but then here's 1, and then it continues greater than 1. So it continues, to infinity. I could also write that as -3 is less than or equal to x, which is less than positive infinity. Whichever method you prefer is fine. This is called interval notation. That's inequality. Locate any intercepts. Ooh, okay. So when we find the intercepts, if I'm looking for my x-intercept, remember back from our first day, if I look for the x-intercept, I set the equation equal to 0. So 0 equals -2x plus 1. And I'm just starting with the top one. I'll have to check here also. So if I solve this, let's see, I would subtract 1, so I get -1 equals -2x. Divide by -2, and I get x equals 1/2. So that tells me my y-intercept is at 1/2. When x is 1/2, y is 0. But let's just make sure, is 1/2 in this interval? And it is in this interval. So that's okay to use this function. I don't need to check for these other ones because when x is 1/2, this is the only interval that works. Okay, my y-intercept, I set x equal to 0. And again, that falls in this interval, so I would say 0 equals -2 times 0 plus 1. Oops, that should be a y, not a 0. Y equals -2 times 0 plus 1. So y equals 0 plus 1 is 1. So my y-intercept is at 0, 1. My x-intercept is at 1/2, 0. It wants us to graph this. So we have to graph the different intervals here. And the way let's start with when x equals 1. When x equals 1, y equals 2. So that's just a single point there. When x is greater than 1, we're going to square this number. Okay, so let's just see. If x equals 1, 1 squared is 1. That point doesn't exist. It's an open circle. Because we start as close as we can get to that. When x is 2, y is 4. And again, if you need to look back at our family of functions, the quadratic simply looks like this. And continues upwards. So when x is greater than 1, this is the piece that defines it. Okay. When x is between -3 and 1, so let's see, when x is -2, we've already found that. When x is -2, y is 5. So I'm just using the blue pen to try and do this. Let's see at the end point, at -3. If I plug that in, -2 times -3 is +6 plus 1 is 7. So I got -3, +7. When x is 0, I think we've plugged that in to find the y-intercept. We had y equals 1. So this looks like a straight line right here. We said when x was 1/2, y was 0. And now we just want to check the end point when x is 1. If I plug a 1 in here, okay, because this is just we get close to this, but we don't actually reach this point. But if I were to plug it in, -2 times 1 is -2 plus 1 gives me a -1. So it's an open circle because we get close to it, but that negative or the +1 is not included in this interval. So here's what my function looks like. Is that continuous? Well, I drew this, had to lift my pen to draw this point, lift it again to draw this part. So no, it is not continuous. Not continuous there. Okay, one last video to get the last example and we'll be done.